For requirement 5, I implemented an API-driven weather system using the OpenMetal API. The purpose is not just to print API data, but to convert real-world weather into meaningful game state changes. The weather system runs through weather cycle actor. After our actor refactor, it extends abstract autonomous actor, so it reuses the shell autonomous turn lifecycle without modifying the engine. Its chosen action only triggers weather cycle scheduler, which controls the update interval and selects a dynamic actual location from worker positions or the weather actual's own location if no worker is present. The API request is built by Weather Query Builder. The request is dynamic because the current map name selects a real-world weather station, and the actual x and y coordinates slightly change the latitude and the longitude, so the API URL is based on current game states, not a fixed static URL. The main coordinator is API-driven weather service. It depends on abstractions instead of concrete classes, weather data provider, weather front, and weather impact. For weather data, I use Resilient Weather Data Provider. It's configured with two weather data provider implementations, OpenMetal Weather Client as the primary provider, and the local weather fallback provider as the fallback provider. So the API-driven weather service asks for weather data. Resilient Weather Data Provider first tries OpenMetal Weather Client. If the real API requests false, it switches to local weather fallback provider and still returns a weather snapshot. This lets the weather system keeps running during network issues. For the main design, I created two key abstractions. The first is weather font. It decides whether a weather condition is active and converts weather snapshot into a weather event. I implemented three concrete fonts: heat wave font, rainstorm font, and the magnetic gale font. Heat wave font activates from hot or dry weather. Rainstorm font activates from precipitation, humidity, or rain-related weather codes. Magnetic gale font activates from strong wind and calculates the downwind direction. The second abstraction is weather impact. It applies the weather events to the game world. I also implemented three concrete impacts: heat wave impact, rainstorm impact, and the magnetic gale impact. Heat wave impact changes the world by evaporating puddles, igniting suitable terrain, and apply overheated status to actors. This shows the output when heat wave happens. Rainstorm impact extinguish fire, flows terrain into puddles or toxic waste, applies soaked status, and can spawn slims. This shows the output when rainstorm happens. Magnetic gale impact applies wind blow status, moves item downwind, suppress fire, and can spawn parasite from gale reaction winds. This shows the output when magnetic gale happens. To avoid instance of checks, grounds use weather trained abilities. For example, a ground can declare that it ignites in haze, flows in rain, or channels magnetic gale. The impact classes ask for these traits instead of depending on concrete ground classes. This keeps the system more open for extension. The weather spawn also reuses our refactored spawn pipeline. In weather service config, rainstorm effect receives a slim spawner and a spawn executor, while magnetic gale impact receives a parasite spawner and a spawn executor. This means weather can trick creature spawning while still applying the same spawn intra effects through spawn effect applier. Overall, this design follows solid principle by separating API feature, weather interpretation, weather execution, terrain capability, and the runtime scheduling. It also satisfies the HD requirement because API data directly changes actors, item, terrain, status, file behavior, and spawning instead of only displaying text.